Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. And in this lecture, I'm going to start with looking at the concept of steady state solutions for a ODE or a system of ODEs. And by a steady state, we mean that in general, as we said before, an ODE is y prime equals f of x and y for one single equation, or y could be a vector, so then f is also a vector which represents a system of differential equations. Okay, now if our variable is x, we want to see what happens when x goes to infinity. And if variable is time, which is basically where the name steady state comes from, when t goes to infinity, or after a very long period of time, what happens to the solutions? Do they reach a constant value and don't change anymore, or are they constantly changing? Obviously, for a system that has a resonant response, like the solutions are sine, cosine, it can never reach a steady state solution, right? Or basically it can never reach a constant solution when the derivatives are zero, because the solutions are oscillatory, they change constantly over time. But there are many systems that can in fact reach a constant solution after a very long period of time, or when the variable x goes to infinity. So we're going to define the steady state solution as this: when our variable x goes to infinity, does our system has a non-zero solution, where so by non-zero solutions we mean that it's a constant solution. So if the solutions reach a constant value, constant level, then we set the ddx to 0 if the variable is x, and then basically this sets the y primes to 0. And then on the right hand side, we have a system of equations. It's not a differential equation anymore, it's just a system of equations. Now these equations can be nonlinear, right? Linear, nonlinear, because when we talked about the ODEs, we said that the right hand side can be anything, right? F of x and y, and it could be any sort of equation. We don't care that much. So we set all the derivatives to 0 on the left hand side, and then find the solution by solving a system of equations, which in general is a nonlinear equations. The steady state solutions are independent of the initial conditions, and in general that's the case. So what this means is that no matter what the initial conditions are, because remember the initial conditions change how the solutions behave, right? But how basically the derivatives start to change, because at the initial point the derivatives are determined by the initial values, right? And after that the function is determined because of its derivatives. But then when the system reaches a steady state, the derivatives are 0 no matter what the initial conditions are, right? So we can conclude that no matter what the initial conditions are, the system will always reach the same steady state solution, and this is very important. And here's an example that I have here. Let's assume I have a system of two equations. y1 and y2 are my state parameters or state variables. So my system is determined by y1 and y2, and they are coupled to each other via this system of ODEs. y1 prime is 2 minus y1 minus y2, and y2 prime is 3y1 minus 5. All right? And first of all, let's look at the steady state solution. In the steady state solution, if the system has such a solution, then we can set the y1 prime to 0, y2 prime to 0, and try to solve the system of equations. So this is a linear equation, very easy to solve. So if y2 prime is 0, y1 is 5 over 3, which is 1.666. And then we put it here in the next equation. 2 minus y1 minus y2 is equal to 0, and y1 is already 5 over 3, so y2 becomes 1 over 3, 0.333. So this system of differential equation does in fact have a steady state solution, a constant solution after a very long period of over the very long interval for the x variable. All right. Now here I'm presenting the solution of the ODE y1 and y2 for different initial conditions. So just bear that in mind. This is different initial conditions. And the point I'm trying to make here is that no matter what the initial conditions are, the system will always reach the same steady state solutions. And it's very clear here. Let's assume that y1 at 0 is 0, y2 at 0 is 0. All right. So what happens here? So first of all, both initial conditions are 0, but we know that y1 prime and y2 prime are not 0, even if both the initial conditions are 0. That if they were both 0, so we didn't have these 2 or 5, then the solution is definitely a constant 0 over time, because the derivatives don't change, the initial conditions are 0, so the system doesn't change. But even if y1 at 0 is 0, y2 at 0 is 0, y1 prime is 2, y2 prime is minus 5 at 0, so the system starts to evolve, starts to change. That's why we see that y1 starts to oscillate, right? But the oscillations eventually die, and y1 reaches a very steady level, a constant level, which is 5/3, 1.666, as we expect. And y1 starts from 0. y2 also starts from 0. Its derivative at 0 is minus 5, so it has a very sharp beginning, and it starts to oscillate, and suddenly it dies off and becomes a constant over a long period of x, 1/3. So this is our steady state solution, steady state, all right? So with this initial condition, the system reached steady state as we expected. And we could, in fact, predict the steady state levels. Now let's change the initial conditions. y1 at 0 is 1, y2 at 0 is 0. So the initial conditions are different. Therefore, the slope of the solutions at x equals 0 is different, right? But again, we see that now the oscillations are different. It goes up for y1, it goes up to 2 before it went up to 2.5. So it goes up from 1 to 2 and a little bit of oscillation, and then dies off and becomes constant. Again, 5/3, 1.666. y2 the same thing, the oscillations are different from before, but again the oscillations eventually die, and then we end up with 1/3, 0.333. So the steady state remains the same. So this is the code I wrote using Runge-Kutta fourth order for solving this differential equation with different initial conditions. So we want to solve y1 prime equals 2 minus y1 minus y2, and y2 prime equals 3y1 minus 5. So we define our state vector, or so z is y1, y2. This is our state vector. Vector here is basically an array, okay? And deriv n function, this is a system of real valued functions, so we call our deriv n function x and z, and we return a double array of 2 elements. The first one is y1 prime, which is 2 minus z0 minus z1. The second one is 3 z0 minus 5, all right? And then initial condition for x is 0, initial condition for y could be anything, right? Here I'm solving for y1 is 1, y2 is 0. And we create our ODE system solver that solves the real valued system of real coefficients and real functions. ODE system solver, we pass in our function deriv n, we pass in our initial condition for x, and we pass in our array of initial conditions for y1 and y2. And then I'm going to solve for x0 to x0 plus 50 and for 1000 points. And then when we call the Runge-Kutta and pass in an array of x values, it returns a two-dimensional double array for z. Each row is all the values of one of the solutions. So z0, row 0 is all the values for the solution of z0, which is y1. So here I'm creating a chart, plot z0 with blue curve, which is y1. So this is y1 solution, and z1 is with color red, which is y2 solution. Render the plot, set the font to 17, x label x, y label is y1 and y2 solutions, and we create the plot. All right. And as you can see, again, the point here is that even with different initial conditions, the transient response is different, but the steady state will remain the same. All right. Now, how do we find the steady state solutions? And as I mentioned, we set all the derivatives on the left-hand side to 0, and then we end up with a system of equations. All right. So we must, and these equations could in fact be any type of linear, nonlinear equations. We might have sine of y1, sine of y2, y2 squared, or whatever. So in general, it's a nonlinear system of equations. Okay. So if it's a nonlinear, first of all, it's a system of equations in general. So we have to have a root finding solution, or a root finding method that has n-dimensional behavior, can solve for n-dimensional. Second of all, a nonlinear means root bracketing most likely doesn't work. All right. So most of the softwares use Newton-Raphson iterations. We've looked at this for one-dimensional case. Now the problem with n-dimensional case for basically Newton-Raphson is that you have to calculate. First of all, it doesn't need root bracketing, right? So that's good. We just start with the initial condition, so that's good. But then the problem is that we need to find derivatives, and in this case the derivatives are actually pretty complex, because we end up with something called the Jacobian matrix. I'm just going to write Jacobian here. So Jacobian means it's a matrix of partial derivatives. So it's not just it's not just one derivative or two derivatives. You have to calculate the derivatives and then the cross derivatives, dy1, dy2. Eventually it gets pretty complicated first, and then the other thing is that numerically calculating derivatives is not easy. Okay, so what do? We use our very powerful particle swarm optimization tool that we wrote in Java. Very simply, it was a very simple algorithm. It's a linear programming. It's just a bunch of summation and multiplications. There is nothing fancy about particle swarm optimization. We don't need any derivatives. We don't need anything. Particle swarm optimization is the best. We're going to find the roots of an n-dimensional function or a system of n equations using our particle swarm optimization. We briefly talked about this when we looked at the particle swarm optimization. Let me just quickly bring it up. So in case for a one-dimensional case, we said that, okay, the way we're going to solve f of x equals 0 for a one-dimensional function f of x, we're going to say that, okay, in general f of x could be crossing the x-axis. Even if it's tangent and not crossing, that's fine. We define a function magnitude of f or absolute value of f. Okay, so if the f does in fact have a root, then that root should be the minimum of the function in the interval that we're looking for, the root, right? Because when we take the absolute value, the negatives becomes positive. So the minimum value can be 0, right? So we said that we take the absolute value of the function, we construct a function based on our original function or original equation, such that its minimum values actually becomes the root. All right. So we find the minimum, and the PSO for minimization is pretty fast, pretty good. No root bracketing, nothing. It just works. And then once we find the minimum of this absolute value, we check whether or not it's in fact the root. So we find the minimum in this interval, we put it in the function and see if it's very close to 0 with some tolerance, 10 to the negative 9 or something. So we're going to do the same thing here. And again, PSO that we wrote, easily we just wrote it. It was very easy to write it for an n-dimensional case, particles with n-dimensional variables. So we already have it there. And then what we do, we just have to translate our system of equations into one single function, because PSO, if you recall, it had one fitness function that was minimizing or maximizing. And we want to ensure that the zeros the solution of our system of equations fi, which is f1, f2. If we have n equations f1, f2, fn, the zeros of these are where the minimum of the fitness function happens. All right, so what we're going to do is that we can just basically do we can do, for example, take the absolute value of each equation f of I equals to 0 and then sum them up, because if there are some functions that are never negative and their sum is 0, then each one of them should be 0. That's at least for real functions, and we know that here we're dealing with real functions, right? When we take the absolute value of a real function or even a complex function, the result is always real, right? So this g of y1, y2, etc., this becomes our basically fitness function for the PSO, and is defined based on, so this is our fitness function for PSO. Okay, and then it becomes 0 if and only if y1, y2 all the way to yn are in fact the solutions are the solutions of the nonlinear system of equations that we need to solve. So when we do this, we have to do the minimization. So PSO must be set to minimization. But the other things that we actually don't know where these happen, right? Because if you recall, PSO requires an initial initial guess for each one of the variables. And we had implemented two types of optimization. One is bounded optimization. So we set the initial interval for each variable, and then the PSO guarantees that the result at the end should be inside that interval. But here we don't want that, because we really don't know the exact solution. We're just looking for the solution. So we do an unbounded search or unbounded optimization. And what it means is that even if we start with the interval that this minimum is not inside that interval, that's fine. The PSO doesn't have to stay in that interval all the time. All right. So we do unbounded optimization. So here's the code. Let's say I want to solve this y1 prime equals 2 minus y1 minus y2 and y2 prime equals 3y1 minus 5. All right. Now, obviously, in order to find the steady state solution, what I need to do is set the derivatives to 0. So y1 prime is 0. So I have one equation, 0 equals 2 minus y1 minus y2. And the other equation is 0 equals 3y1 minus 5. And I need to solve this system of two equations. So I define my fitness function for the PSO, and it takes an array T. Remember, T is an n-dimensional array. And then I set the T0 as y1 and T1 as y2. So the first one, because the first equation becomes the absolute value of 2 minus T0 minus T1. The second equation, so I add them together, plus absolute value of 3 T0 minus 5. All right. So if I minimize this, the minimum must be the solution of these two equations, because each one of these absolute values must independently be 0. And I create my PSO, new PSO, 100 particles, passing my fitness function, and then initial intervals for each variable, T0 and T1. And again, it doesn't really matter, the intervals, because we're doing an unbounded search, unbounded optimization. So the PSO doesn't have to guarantee that the solution eventually is inside these intervals. So we just set them to something like minus 100 to 100, minus 100 to 100. All right. And then I definitely want to do minimization. So set minimize to true, set bounded optimization to false. And I believe the default was also false, but it's good to make sure that it's always false. And this is very important, because we actually don't know whether or not the solutions are inside these initial intervals. And then I do solve and plot. The reason I'm plotting the convergence or the values of the fitness function for the iterations, right? For the number of iterations. And then best position is basically T value, right? T vector, T array. It prints the T0 and T1. So before, so here, so what we have here is that if I do set if I run the solve and plot for 100 iterations, so I have 100 particles with 100 iterations, the result is very fast, almost takes no time, because we're not doing any calculation of the derivatives, Jacobian or etc. And here's the convergence. So if there is a steady state solution for our system of ODEs, which means if the fitness function does in fact results in a minimum, if a minimum exists for the fitness function, then we should see a very nice convergence, and here we see that. So our fitness function, the PSO with an unbounded optimization, definitely reaches a steady state. Basically, it brings the fitness function to 0, and that's what we want, right? Because we already know that absolute value of something plus absolute value of another thing, if it has a solution, if it's equal to 0, if it has a solution, it can only be 0, right? And we hit this 0, the value of the best value is basically the value of the fitness function. So we definitely hit a solution for this system. And before going to the next slide, I'm going to reiterate that if a steady state solution exists, the PSO minimization will find it, and we can clearly see whether or not it exists if we see a nice convergence in the fitness function and it goes to 0. We can check by looking at the convergence of PSO and whether or not the value of the fitness function does in fact go to 0, right? It has to go to 0. So here's the let's head to Eclipse and try to run this code. In our Eclipse, in our ODE project, ODE package, we have all the interfaces, all the classes, and in the test I have this test steady state solution, and test 1 is basically the code. So deriv n function, this is my system of equations, initial conditions. This basically solves the solution, right? So this solves the ODE with any initial condition that I said. So right now it's 1, 0, and we see that it goes to 5/3 and 1/3, right? 3.3 and then 166. Now let's change it, for example, to 1 and 1. Let's run it again. Again, 1.666, and the transient response, this part is different, right? We start from 1 and 1, and then it has some oscillations and eventually reaches the steady state. Here we start from 1 and 0, and we reach the same steady state. So no matter the initial conditions, we definitely reach a steady state. Now in test 2, we're going to find the steady state directly by solving the equation, right? So this is our PSO fitness function, ABS of 2 minus T0 minus T1 plus ABS of 3 T0 minus 5. We create our 100 particles, we set initial interval, set minimization to true, set bounded optimization to false, 100 iterations, and we looked at the best position, right? So as you can see, we reach for T0 or Y1, we end up with 1.666, 5/3 as expected, and for Y2, which is T1, we end up with 0.333, which is 1/3 as expected. And as you can see, we get a great convergence, right? And it doesn't really take that much time, so it's pretty fast. PSO for finding roots is pretty fast. In general, PSO for minimization is pretty fast, so that's a good thing. And then the next thing about the steady state solutions is that a system may have more than one steady state solution, right? Now in this example, the system is just linear equations, so it either has no solution, one unique solution, or infinite solution, and we saw that, yeah, the system has one unique solution. But what if the right hand side of one of the equations is nonlinear? In general, we might end up with more than one solution. And what determines which steady state will be reached by the system of equations? It's the combination of the ODE itself, how it behaves, like the stability analysis of the ODE, and also the initial conditions where the system starts to evolve from. All right, so the evolution of the system and the stability of the system itself. For example, if an ODE doesn't ever oscillate, doesn't have any oscillatory solutions, and it always ends up with the growing or decaying exponentials, there's definitely no steady state solution unless we all of this no, in fact it can reach a steady state solution if all the solutions end up with only decaying exponentials, right? If a system allows for growing exponentials but it can never reach a steady state solution. So here's a system which is similar to the previous one, but instead of having 3y1 minus 5, I have 3y1 squared minus 5. Now we have two steady state solutions, because now if I set y2 prime to 0, I end up with y1 equals plus minus square root of 5 over 3, all right, which is plus minus 1.291. So I have two solutions for y1, and then if I set y1 prime to 0, I end up with two solutions for y2, which is 2 minus y1. One is 0.709 and the other one is 3.291. All right, and again we can find all the solutions. I mean, the way I'm doing it here in this code, I'm creating a list of double values for y1 steady state, y2 steady state values. I just run the PSO 50 times, right? Now, obviously this is not the best way to search for all the solutions, but what I hope here is that when I run it for 50 times, because PSO, the start point of the optimization in these intervals is random, right? It randomly picks a number for initial value of the y1 and initial value of the y2 in the PSO optimization. So what I'm hoping is that after 50 times of randomly running the PSO, it probably hits or reaches both of these minimum values. That's why I'm hoping to get both of the steady state solutions, and it does in fact picks up on both of the solutions. So PSO is the same. After solving for 100 iterations with 100 particles, I just add the solution for y1, which is t0, and then a solution for y2, which is t1, and then I just plot them, right? y1 versus y2, because I want to look at the state diagram y2 versus y1. And we clearly see only 2 points, which means it does in fact have two steady state solutions. But if you look at the ODE itself and analyze its stability, you see that this steady state is oscillatory. It has an oscillatory transient response. So the system can in fact oscillate a little bit and then reach this state. But this one doesn't have any oscillatory solutions, which means that the system before reaching this, it does in fact, the solutions in fact diverge before reaching this. So based on the initial conditions. So these solutions can never be reached, this steady state solution. So let's head to Eclipse and try to look at this code. So this one is test 3. So let's run test 3. And in test 3, what I'm doing is basically creating a list of double values, two array lists, and running the PSO 50 times, hoping that eventually when I run it randomly, I end up with all the solutions, all the minima of this fitness function, which I do. And then I create a chart, plot y2 versus y1, render it, set the line width to 0, set the font to 20, and then let's plot. Yeah, as you can see, this is 1 point and this is another point. All right, so we end up with 2 points. Now what happens if, for example, we change our equation a little bit? Let's say t0, and here we also have t0. So if t0 squared is 5 over 3, then t1, so we only should have only one steady state solution. As you can see, so we have two steady state solutions, because t0 can be plus or negative square root of 5 over 3, right? But for either of these values, T1 is always 2 minus 5 over 3, which is 0.33. So we have two steady state solutions pretty much at the same level for y2, all right? And let's say now we have, instead of this, we have T1 squared. So T0 can have two values, and then for each of those values, T1 can have two values. So we should end up with 4 steady state solutions, which is indeed the case, right? So this is plus square root of 5 over 3, and this is minus square root of 5 over 3. So y1 steady states are plus minus each other, and y2 steady states are also plus minus each other. So we have 4, right? Now again, what determines which steady state solution the system can in fact reach is the initial conditions, all right? So what I'm going to show you here is that if we start with our solution, or 3y1 squared minus 5, 2 minus y1 minus y2, this is our original example, and let's look at the test 4, which is solving this system of equations, 3y1 squared minus 5, 2y1 minus y2. So here we have y1 squared, and this is our deriv n function, 2 minus z0 minus z1. Z is our vector, basically our state vector, and 3z0 squared minus 5, initial condition 0, and initial conditions for y1, y2, let's say 1 and 0, all right? And we're solving the ODE for x0 to x0 plus 50 using Runge-Kutta fourth order. See, we have the oscillations and we reach the steady state. One of the steady states is basically square root of one of the steady state is 1.291, the other one is 0.709. So 1.291 and the other one is 709, okay? And we have some oscillations around, and so let's change the initial condition, for example -1. You see we still get the basically we still get the same steady state, right? 1.291, and then but then the initial conditions are different. We see the oscillatory behavior. We start from -1, we start from 0, okay? Everything is good. But the question is, can we reach the other steady state? So if I want to reach the other steady state, y1, let's try to make it large, let's say 4, right? Because the steady state solution is -1.29. And let's also keep this as 0, for example. So we hope to reach the steady state solution for the second solution. Let's see what happens. As you can see, in fact the solution starts to diverge, or the system becomes unstable. So as you can see, we have a exponential that growing very fast, and both solutions end up with a growing exponentials. One of them is positive, the other one is negative. No oscillation happens, so the system becomes unstable and the solution in fact diverges, right? So pretty much no oscillation. If I set this, for example, to minus or maybe 10, again the same thing, the solutions start to grow exponentially. So before reaching the second steady state solution, the system in fact diverges, and it's not possible to reach the second steady state solution. So steady state solutions are not just about the initial conditions. The behavior of the ODE itself can also determine whether or not the system is able to reach a particular steady state solution. All right? So I hope you enjoyed this lecture, and I'll see you in the next one.